This is my experiment. Okay, I have a source which is about 10 volts and 40 megahertz. It's a sinusoidal source. Internal resistance of the source is 50 ohm. I connected light bulb to this. Okay, the light bulb is on, right? That's 10 volts. That's a lot of voltage. Okay. Now what I'm going to do is I have this transmission line. It's an open line, right? It's open on both ends. I'm going to connect this transmission line in parallel with that. This is the transmission line in parallel with this light bulb. Okay. What's going to happen to this light? Do you think that it will affect this brightness of this light bulb at all? From your circuit theory that you've learned. Okay. What is going to happen if I connect this? It's an open circuit, right? This end is open. There's two wires. One is in the middle. That's this wire. The other is a shield, which is this wire. Okay? And it's connected in parallel with this light bulb. Okay? What's going to happen to this light? That's the question. Okay? Okay? And then any other solutions? Think about the solution. Okay? What? The light will be turned off. Light will be turned off. So there's three possibilities, right? Maybe four. I'm not sure. The light will not change. It will be off and in between, right? Or maybe it's brighter. Maybe it's brighter. Who knows? Okay. All right. It's been turned off. Okay. This is open. Okay. All right. What if I made the short circuit here? I'm going to short circuit this part, right? So if you look at my circuit so far, I have a source here, I have my light bulb here, the lamp is here. I have a line, which is this. It's about 1 meter long. Okay, it's about maybe a little bit long. Well, it's about 1 meter. Okay. When I connect this with the light bulb, the light is off. Okay. When I disconnect this, the light is on. Okay. When I connect this, the light is off. It's like magic, right? What if I short circuit here? What's going to happen?
The battery will dead.
What's that? I need to borrow a key. You have a key? Because I don't have a key. Okay. This is a random key, right? We're not doing magic, right? You're not helping me, right? What happened? It's on, right? It's off. It doesn't make sense. It's not. Ohm's law does not apply here, right? So that's what we're going to. Ohm's law field. Okay. This is a random key. It's his key, it's not mine. Okay, so, and this is very simple. What do you think? What's happening? What do you think is what is happening here? Okay, so I have open circuit, the lamp is off. I have a short circuit, the lamp is on. Okay. What if I connect this to another open line? What's going to happen?
It's hard to say.
It's off, right? It's another open line. And this is exactly what we want to study. Okay. So what happened is I connected to another open line. It's about another 1 meter line, and the lamp is on. Ah, very good experiment. Yeah, try it. No, you have to connect it to the center and the side. Yeah. Yeah. Now if I connect this, it's a little bit, it's not off, but it's a bit dim, right? See? Okay.
What if you connect to a third line?
Yeah, good question. Yeah, what if you connect the third line? So now we can apply this. This is physics. Then we can use theory to explain what's happening. Okay. All right. The source right now is what is this frequency? 39 megahertz, right? Okay. 39 megahertz, sinusoidal. Okay. So I basically use this as a switch. It's off, and then it's on. Okay. So what happened is this is the transmission line. That's why Ohm's law does not apply. Basically, what happened is, okay. So if I use Ohm's law, okay, if I make a short circuit here, okay, and basically the current here is going to be infinity, right? And this is the voltage here, and so voltage over resistance is current. That's Ohm's law, right? Yeah. And that does not apply anymore because V of t at time t, these two are not associated with that Ohm's law. Okay, they're not associated. This time t here and this time t here, they're not associated with this Ohm's law. You cannot, this equation does not apply because there's a time delay between these two. Okay, there's a time delay. Okay, so you so this is called the transmission line. Okay, because the sinusoidal waveform has a frequency of 39 megahertz. Okay, and in general, and the wavelength. Okay, what's the speed of light?
About 3
Its speed of light is 3 times 10 to the 8th meters per second. Right? That's the speed of light. Okay. So when we calculate the waveform with megahertz, if I use megahertz here, okay, I can just use 300 meters, and then it's 39. This will give me waveform. Okay, in meter, because this is megahertz. Notice that this is 300 times 10 to the 6th meters, right? Meter second. So this two will cancel each other. So it'd be 300 divided by 39. That will give me maybe 40. So it's about 7 meters, right? 7.5 meters. Okay. This is the waveform in vacuum, in free space. Okay. But in a cable, most cables are so-called 60% cables. Okay. Some cables will tell you the speed of the cable. This one doesn't have any marker. So usually the speed of the way electromagnetic wave travels inside the cable is much slower than the speed of light. It's about 60% of the speed of light. Okay. All right. So basically, let's say it's 60%. Okay. So it'll be about 200 meters, right? Okay. Instead of 300 meters. So over here it's going to be 200 meters. So this 60% of speed of light. Okay. And then over here it's going to be about 5 meters, right? So, and then 1 meter is more or less close to about 1/4 of the wave, right? So this is about 1 meter is 1/4 of the wavelength closely, a little bit more than that, okay? So basically, if I draw one wavelength of this wave, okay? If I draw one wavelength of this wave, it's going to be 5 meters, right? Okay, it's going to be 5 meters. So if I take a snapshot of this wave on this, I cannot. This is open, so if this is open, it's going to be something like this, right? This is just a half of that. So a sinusoidal waveform. This is one wavelength, okay, and this is one half of that wavelength, okay, because this is open, so you have the highest voltage at this point because there's no current, okay, so the voltage is highest. So basically, there's a peak here, and then when it goes to here, you're going to have a negative peak, but the voltage here is not going to be zero, okay, it's going to be negative peak. That's why, is that right? So our theory, this is our theory. That's why when we connect these two lines together, the light is on because the voltage is not zero, right? At this point, it's negative, but it's not zero. Okay, but if we have just half of that, then how do we draw? We will still have maximum voltage at this point, right? Yeah, maximum voltage at this point. But this is one fourth away, 1/4 of the waveform away from here. So now what's the voltage? It's going to be like this. Got it? Okay, so this is 1/4. So if you have maximum at the end here, then at the source, you're going to have a very small voltage. Okay, that's the wave propagation. That's how the wave propagates. Okay, and yes.
Why don't you discuss the point on the bottom? I mean, if I can see the upper point, the voltage in the upper point is zero, but if the voltage on the jump point is not zero, then that can still be turned on.
No, we're assuming this is 0 volts reference. Okay, this is 0 volts reference. This voltage is compared to this line. Okay, at this point, voltage is between these two. That's the voltage, right? And this is space. This is distance in space. Because this is open, this end is open circuit, so voltage will reach its maximum because there's no current here. Okay, And so when the voltage reaches maximum here, then 1/4 of the distance away, and that voltage is 0. Okay. But if I make a short circuit here, then this voltage becomes 0. Then 1/4 quarter the wavelengths away, you're going to have a maximum voltage. Okay, that's why when can I borrow your key again? See, that's why. See, the voltage is 0 at this point right now because this is one quarter wavelengths away, right? But if I short circuit here, you can see that I get this voltage there. So we have to use wave propagation to explain this. Okay, we cannot use. Yes, you don't understand? Because there's no current, but there's an energy propagation, right? And the energy is V times I. That's power. So when the power reaches that point, and then because current is 0, so voltage becomes maximum. Yeah. No, the energy is going to be reflected all back. Yeah. There's a reflection. There's a total reflection. Why the voltage here is highest? Because power is VI, right? Power is VI. Because there's no current here. So the voltage becomes maximum because the power is still the same. Because assuming this line does not consume any power, this is power transmission. This line is assuming this line does not consume any power. So the power on this cable is still there. It's a total reflection. It's a total reflection. Yeah, it is hard to think. Okay, it's like water wave that hit a cliff. When the water wave hit the cliff, it will reflect, right? At that point, you get maximum wave, right? Because basically it's double the wave. Okay? If you have a water wave that goes and hit a cliff, at this point you're going to have a higher wave than you have reflection. It's the same concept. Okay, the same concept.
That makes sense, but I think the same thing will happen on the jump line, and the energy will also reflect back.
Yes, energy. Yeah, energy actually travels along both lines and come back along both lines. Yeah, that's another concept that this is the first concept I want you to learn, because this is really different from circuit theory. Because you can see your circuit theory does not apply anymore, right? You put a short circuit here, that light bulb is on. You put an open circuit here, that light bulb is off. That's not your circuit theory, right? Because it's a wave propagation.
But it's still a little confusing because since the energies can reflect on both lines.
Yes.
But why the voltage on the down line we assume it's 0.
We'll just assume, that's assumption. We use the bottom line as a reference. Okay, so we use the bottom line as a reference. We check the voltage on this line, how high, how low this is compared to this. It's a reference. Just like if you use this, you can see that you get a negative, positive. How do you know it's negative or positive? Because you have a reference line. Okay.
Is this means that end is also 0 voltage?
This is 0 voltage here. This is 0.
The other open.
This one?
Yes.
Yeah.
The lower one.
The voltage here is 0. Yeah. Because if you draw if you draw this continuously. Oh, wait. No, that's not true, sorry. This is not 0, this is this. This is going to have this curve. That's this line. If you have two lines, you have you extend this one more 1 meter long, you have a highest voltage at this point. Then, because it's a sinusoidal wave, right? So at this point, you're going to get a negative maximum. But the lamp doesn't care you have negative or positive, it will be just on, right? The current goes in both directions.
As you say that, whatever the line is so long.
Say it again.
Whatever the line is 1 meter, 2 meters, or 3 meters. The end of the ladder is always the highest.
Yeah, if you have an open circuit, yes. If you have open circuit here, at this point you always have a maximum voltage. That's why now you can see it's on.
But what happens if I don't assume that downline is 0 voltage? Actually, below 0%.
It doesn't matter. It's a reference. Then the other voltage will change accordingly. Yeah. It's wave propagation. So, because this wave can only travel at certain speed. Okay. In this case, the speed of light is very interesting. Do you know how long the speed of the light travel to 1 foot? How much time does it take for light to travel to 1 foot? This long. It's 1 nanosecond. Okay. That's also very interesting. Okay. So if you turn on your LED here, 1 nanosecond later, the light reaches this point. And it's very funny because that foot actually is somebody's foot. You know, it's one of the kings of England. It's his foot. And his foot just exactly have this property where, you know, the light travels within 1 nanosecond. I don't know why this is so interesting, you know. So that's the speed of light. Okay, that's the speed of light. Of course, in a cable, it'll take 1.5 nanosecond, well maybe 1.4 nanosecond for light to travel in that cable, because nothing travels faster than the speed of light, right? It's always slow than speed of light. Okay, and this is a very important concept that I want you to learn, because it's really very confusing if you've seen this for the first time. It's very hard to explain what's going on. Okay, because energy takes time to travel. Okay, and then of course we're all bounded by the speed of light. Nothing can travel faster than the speed of light. Okay. All right. I'm going to explain to you a second concept where energy actually travels inside this cable along both lines, not on the same line. Okay. So that's another concept I'm going to explain to you a little bit later. Okay. So and yeah, just think about it. It's kind of interesting, but it's a new concept. It takes a little bit of time for you to appreciate this. Okay, all right. But it's a very, very simple, very effective experiment. Okay, I like it very much.